Let's take a look at homework problem out of section 4.3, number 54. It gives us an equation like f of x is equal to x minus 17 inverse tangent of x. And it asks us questions based upon the first derivative test for the interval of this function from negative 4 on the root of 3 to 4 on the root of 3. Okay, so first derivative test is based upon the critical points of the function, where we break up a function's domain with its critical points to find when the function is increasing and to find when the function is decreasing. Excuse me. So, okay, in this problem, I went ahead, I took the first derivative. Derivative of x is 1. And then, of course, we know that the derivative of 17 inverse tangent of x is going to be 17 times the group of the derivative of the inverse tangent, which is 1 over 1 plus x squared. So I get my derivative is 1 minus 17 times the group, 1 over 1 plus x squared. I set that equal to 0 with the intent of finding the critical points. Remember, those critical points are the points at which your original function flattens off. It could attain a maximum or a minimum at those points. So we can say, well, in order to find those points in this equation, we go ahead, set this equal to 0. When I set it equal to 0, I went ahead and just added the 17 over 1 plus x squared to the right-hand side, solved that equal to 1. Now, I multiplied by 1 plus x squared on both sides. That just gave me a 17 on the right. 1 times 1 plus x squared on the left gave me 1 plus x squared on the left. That made it very easy to solve for x squared. Just subtracted 1 on each side. X squared is equal to 16. Please remember here, whenever x squared is equal to 16, x can both equal the positive or negative root of 16. So you say, well, your critical points are going to be at plus and minus 4. These are the only values at which my function flattens off and could attain a maximum or a minimum value on this interval. Well, in fact, overall for this function. So what I do is I take the domain of this restricted domain function, and I say, well, we're going to start at negative 4 on the root of 3. We're going to go up to that first critical point of negative 4. That's going to be our first test interval. Then I'm going to start at that critical point of negative 4, go to the next critical point, 4, and then I'm going to go from that next critical point, 4, to the end at 4 on the root of 3. Anytime you have 2 critical points, you're going to have 3 test intervals. It just breaks the domain up with those critical points. Now, I need to choose a test point in each of these intervals. I know negative 5 is to the left of negative 4 and it's to the right of negative 4 on the root of 3. I chose that. Negative 6 would have been fine. There's nothing special about negative 5 other than it is in the interval that it's supposed to represent. A number between negative 4 and 4, I chose 0. And a number between 4 and 4 on the root of 3, I chose 5. Now, what we're interested in is what is the sign of the first derivative in each of these intervals. Anytime the first derivative is positive, you know your function is increasing. Anytime the first derivative is negative, you know your function's decreasing. So when I plugged these in to the first derivative here, you'll notice I didn't put the specific number. You could have. When I plug a negative 5 into this, it would really give me 1 minus 17 over 26. That would give me a 17 over 26, 26 over 26 minus 17 over 26. It'd give me 9 over 26. The only thing I care about, though, is that it is a positive 9 over 26. So I'm trying to emphasize that by only putting the sign of the answer when I plug each of these test points into my first derivative. When I plug a 0 in, of course, we just get 1 minus 17, and 1 minus 17 is going to give me a negative 16. That's why my sign is negative there. And when you plug a 5 in, you get the same thing as when you plug a negative 5 in. You'll get 1 minus 17 over 26. It's going to be a positive 9 over 26. Now, whenever the first derivative is positive, you know your function is increasing. When the first derivative is negative, you know your function is decreasing. Again, here, first derivative positive, your function is increasing. So even before I went to my calculator to graph this function, I knew it had a local maximum at -4, because what this is telling us is that it's increasing before -4 and it flattens out at -4. It decreases in between -4 and 4, and then it's going to increase after 4. These are the only 2 points where the graph flattens off, and you know that since the derivative is positive before this one, it's increasing. It's negative in between, so it decreased down to 4, and then it increased after. Now, to answer part B, part A is your x equals positive and -4. Part B is just going to be where are your local maximum and minimums. I have a local maximum at the critical point between where it increased and decreased. So you know -4 is a maximum. And then I have another critical point between two intervals where it decreased before it, increased after it. So it had to be a minimum. So I know I have to have a maximum at -4. I have to have a minimum at 4. Now, in order to answer part C of this one, you really do need to graph it out, because when it's asking absolute maximums or minimums, the absolute maximum or minimum, it could be at the critical point or at the end point. So I went ahead and just graphed my function, and I went to a little to the left of -4 on the root of 3 and a little to the right of 4 on the root of 3. So I said, let's graph this function, f of x, on x equals -8 to 8, and then to get the y values that I got, all you have to do is hit zoom 0. When you do this, this should be the function that you get into your calculator. If you hit trace -4, it's going to yield this maximum right here, and we can see that the function is always going to be lower than that. When you hit trace 4, you're going to get this local minimum down here, and then the corresponding y value for that. And we know it's never lower. So in this case, the local maximum and local minimum are also your absolute maximum and minimum on this interval. So I can say I am confident in saying the same answer for C that I have for B. The absolute maximum minimum, same as the locals in this problem. All right, this is a good question. Let me know if you have any problems with others like this.